Now let's turn to problems that involve two or more media. So this means we have to understand how the electric field, the electric flux density, how they behave at an interface, or the boundary between two different media. So we're going to consider a point P. So we'll just quickly say, let's consider problems involving two or more media. We take a look at an arbitrary point P lying on the interface or boundary between the two arbitrary media 1 and 2. So let's quickly draw a diagram of what this looks like. We have some sort of interface. Made this too big. So we have an interface. We have medium 1 over here and medium 2 below. And we're going to take a look at a point P over here. So this is an arbitrary point P on the boundary between two media. So there's also going to be an electric field vector for each one. So we have, let's say, the electric field for media 2 and the electric field for media 1. Now, taking a look at this, all we're really trying to get from here are some boundary conditions. So if we can determine some boundary conditions, these conditions and equations will really help us out when we try to solve problems involving different media at an interface. So there's two different conditions we want to look at. We want to take a look at the tangential boundary condition and the normal boundary condition. So essentially this means we're going to break down our analysis into two pieces. We're going to take a look at the electric field, and we're going to take a look at the electric flux density and just take a look at their tangential and normal components to see if there's any information we can get from that. So using our knowledge from the previous chapter on conductors and boundary conditions, why don't we construct a closed contour around P? So what this closed contour means is we're going to just create a box around the boundary. So it's a path from A to B to C to D to A. It's a closed path. It has a length of delta L, and it has a height of alpha. So I'm going to take a look at the tangential boundary condition first, because if we remember, as we get closer and closer to the boundary, that height, alpha, is going to get smaller and smaller, and that means we're going to look at the tangential components. So let's just quickly say we have a line integral for that closed path A, B, C, D, A, and that is integral E dotted with dl. So we're going to make delta L parallel to the horizontal boundary. So delta L is parallel to the horizontal boundary when it is very small and essentially no curvature is detected whatsoever. We're essentially going to make alpha go to 0 so that it doesn't contribute to the line integral and doesn't introduce a normal component. So then looking at E1 and E2, we have the integral of E dotted with dl being equal to, now we have the tangential component or the x component of the first electric field, so E1t, minus E2t delta L is equal to 0. So that means in order for this to work, we just have E1t is equal to E2t. So what this tells us is that the tangential component of the electric field is continuous across the boundary. So just to repeat, we do have alpha times delta L being the area of this. Essentially, if you're going through the line integral, you're going to have a portion of that integral going in one direction. So let me just draw this. We can go A to B to C to D back to A. So I'm taking a look at the tangential components. If we go from B to C, because the vertical components are now going towards 0, so if we go from B to C in one direction, the same length delta L goes from D to A, and so those two subtracted from each other should equal to 0. Okay, so we've taken a look at the tangential boundary condition. We now want to take a look at the normal boundary condition. And with the normal boundary condition, the first thing we want to do is apply Gauss' law across the boundary. So let's, in blue, draw our boundary, or the interface. We have media 1, medium 2. And applying Gauss' law through that boundary surface or interface, we can use a cylinder. Like this. And we're going to call the surface area delta S. And we want to make this small. We also note that we should calculate the electric flux density, or take a look at the electric flux density. So let's assume the electric flux density is going to be like this. And then we have this going like this for D2n for the normal component to the boundary. Next we have the normal vector from the surface, which is going to be A2n, points outside of the surface and points outwards of the surface here. So we have A1n on this side. Once again, we have some height, alpha. It goes to 0 because it makes no contribution to our calculations, which makes sense because we're trying to get closer and closer to our boundary. And now we simply take a look at d dotted with ds. So the integral of d dotted with ds is going to be d1n minus d2n, so a change in the electric flux density times a change in S. And all of that is going to be equal to the enclosed free charge, which is going to be some sort of charge density S times delta S. So now our delta S's can cancel, and we have rho S being equal to d1n minus d2n. So this is an important relationship, but there's something else we haven't analyzed that yet, and that is rho S. So in a dielectric interface, if we have no free charges on the boundary, then rho S free is going to be equal to 0, and then d1n is equal to d2n. So the condition is we have d is continuous. So this would be our normal boundary condition. We can state that d is continuous at a dielectric interface because there is no free charge. So now we've covered the two different boundary conditions, and we can take advantage of these when we approach different problems related to dielectric interfaces.